now let's, I guess I should see if there are any, this is really more introductory material, but if there are any other questions to which I can encourage you to go look at more specific literature, then now's a good time to raise your hand. Otherwise, what I'm going to do in the remaining part of these lectures is to describe a different approach. And where we stand at the moment, you can think of it as the longer and perhaps more scenic approach. Since we're going to be studying only above threshold observables, only unbound observables, and how to do this in the bound state context is still in the future. So the basic idea of the approach is very much in the philosophy of scattering amplitudes, is that you want to pick some well-defined observables in the quantum theory that are also relevant classically. And then we're going to see how to express them in terms of scattering amplitudes. And that will then bring in, if we're looking at observables in electromagnetism, bring in QED scattering amplitudes, or if we're looking at gravitational observables, gravitational scattering amplitudes. And that would be the place that one can take advantage of the Kawhi-Llewellyn-Tie or double copy relations. And once one has expressed them in terms of scattering amplitudes in the quantum theory, then we're going to understand how to take the classical limit efficiently. So there's a lot of conceptual material that I think is valuable to understand that won't ultimately play a role in explicit calculations, but and I am going to try to cover that conceptual material in a lot of detail, rather than going through the nitty-gritty of calculations at the board, although I am going to try to do a couple of examples. So the setup that we have is kind of the unbound analog of the caricatures I was drawing earlier. We're going to scatter two point particles. And so we have two point particles, and they're going to be going this way. And of course, under the influence of the force, they're ultimately there's going to be a deviation, and there will be a scattering angle. And there's going to be some impact parameter. We're not going to shoot them head on at each other. And that impact parameter, for some historical reason, is usually called B. So we're going to assume that these particles are distinguishable and that they carry separately conserved quantum numbers. So maybe they carry some global charge, or they have different charges in QED. And we're primarily going to look at the first of these two observables, but we'll look at two observables. And the second one will depend a little bit on how much time is left on Friday. One is the change in the momentum, the time-integrated change in the momentum of one of the particles, let's say particle 1. And this in classical physics is known as the impulse. And the other is that the total momentum that is radiated during the scattering. That, of course, is closer to what we're interested in terms of the gravitational waves. Now, we all love scattering amplitudes, or at least those of us in the scattering amplitudes community do. But at the end of the day, they are gauge invariant and nice objects, but they're not necessarily the final goal, and they're not necessarily physically meaningful on their own. So what we're going to need to do is construct observables like this and then express them in terms of amplitudes or combinations of amplitudes, and really focus on the things that are physically observable. So we're going to want to take a classical limit, and usually the conventions that one employs in quantum field theory, of course, is h bar equals 1. And we don't actually want to take 1 to 0. So instead, what we need to do is to reintroduce the powers of h bar back into our scattering amplitudes. And this is basically an exercise in dimensional analysis. I should say that we're going to stay fully relativistic. There's no need to necessarily go to any small velocity expansion. So we're going to keep c equals 1. And if you actually want the powers of c in order to compare with people who put them in for some obscure reason, then you just do the required dimensional analysis. So one of the things that's different from usual conventions in quantum field theory is that dimensions of mass are no longer the same as the dimensions of inverse length. We can still choose the normalization of momentum eigenstates to be the same as in quantum field theory. And that means that the dimension of an endpoint amplitude, n here including both the incoming and outgoing particles, remains the same as in field theory. So if you think back to your first lecture of quantum field theory, before the lecture went to natural units, then you'll recall that there's an h bar in alpha, and that reflects the fact that there's actually an h bar in the couplings. So we have to put in an h bar for every factor of the QED coupling E, that's for photon couplings. And likewise, for the gravitational coupling, mercifully, it's the same factor of h bar. And I will call these collectively messengers. So when I refer to messengers, I will be thinking about the massless force carriers. And when I want to refer to them collectively, then again, we're going to I'll just use G. So this is generic. Now,
David, can you once again explain why E scales like E upon H cross?
It's just the dimensions.
In the action, usually like e to the power I s upon H cross path integral appears. So, and the coupling constant usually scales so like 1 over H cross.
The E on the left is the E that you would write down when you're setting H bar equal to 0, and then I want to replace that with an appropriately dimensioned E that has all the explicit powers of H bar removed or made explicit, and that's the object on the right-hand side of the right arrow.
Okay, thank you.
So I mean, this is not an equality. It's kind of making manifest the powers of H bar, and then after I've made them manifest, there's no more hidden powers of H bar. Now, the other thing that we're going to need to do is to distinguish the wave number from the momentum. And so to do that, we're going to introduce again a notation. So P bar is going to be P over H bar. And this again is the original momentum. And this is the wave number. Okay, so, well, so far we just have some H bars that are coming out of the couplings. It's pretty straightforward to count the couplings because the endpoint tree amplitude, let's say in QED, scales like e to the n-2. And if we go to an L loop amplitude, then it'll scale like e to the n-2 times e to the 2L. And so we're not actually that concerned with E at the moment, we're concerned with H bar. So if we have an endpoint L loop amplitude then that object scales like H bar to the 1 minus n over 2 minus L. And some of you are probably going to be a little bit disturbed because this seems to be singular. And it will take us probably about an hour and a half to understand why you can relax. And this is not the whole story, of course, although there are some very eminent French classical general relativists who are confused by this point. So if you're a little bit confused, you're in very good company. Now, the first step in understanding how to get out of this confusion and this seemingly singular behavior is to realize that we are not doing usual kind of collider physics. So there, in collider physics, one is usually interested in plane wave states. And that is inappropriate for us because we need to have spatially localized states. So we have to build them out of a superposition. So we're going to build a wave packet out of plane wave states. So the plane wave states, again, if they're a single particle, then they're the usual plane wave states of quantum field theory. I'll put in a subscript here to denote that we're talking about the incoming states, which is where we really control the scattering experiment. And so the one particle state, well, we want this thing to represent an on-shell particle. So it's natural to build this out of an integration over on-shell states. So we can start to write down integration over all momenta. And probably most people know what everything is here, but I will just say it out loud just in case. So we have a Lorentz invariant phase space measure, and over here, and we have the on-shell delta function over here. And just as a reminder, the plus means you take the positive energy solutions to the, out of the two solutions to the delta function. So I get tired of writing out and also seeing the visual clutter of pies. So I'm going to introduce a shorthand notation that hides all those pies away, and you only need to reveal them at the very end of the calculation. So let's use a hat for the measure, and also a hat for the delta function. And then we can write our incoming state as visually a little bit cleaner form. Why it does that at the bottom of the screen. Of course, the meat of the shape of the incoming state is in this wave function phi. So this is our one particle state. And that tells us, if you follow through the dimensional analysis, then you're going to want a wave function here that has a normalization of 1 over mass. So we want, of course, an incoming state that has two particles in it. And so we can write down our incoming state, which I'll call psi. And we now have to integrate over both of the two particles. So I'm going to use this notation now to stand for d hat for p. So d phi of p times the positive energy on shell delta function, more abbreviation. So we have to integrate over both the incoming particles. We have wave functions for both of them. They could be different. You can choose them to have the same form. Won't actually play a very significant role. There's an impact parameter. So that reflected in a phase, a relative phase of the two wave functions that we put together. Of course, the plane wave state is just a tensor product of those two, of the two incoming states. So we're going to want to normalize that state to have unit normalization. That's the most convenient. Of course, the end result doesn't really matter how you normalize it. You just have to divide by that if you don't normalize it this way. And that's basically going to tell us that we have a normalization condition that says that the square of the wave function should be equal to 1. You get a delta function from the momentum state overlap, and that collapses the double integral to a single integral. And then this is the correct normalization condition. Okay, so now we can start to build observables. So the first thing we should do is to look at what the final momentum, again, if we're focusing on the impulse of particle 1, we should look at the final momentum of particle 1, and then ultimately we'll subtract off the initial momentum. So that expectation value, again, we're working in a quantum theory, so here
David, I have
yes.
a question. Like,
yes.
When you define the in state, are you fixing the position of the second particle, and
we're fixing the group momentum, right? So I haven't said much about phi here, the little phi of p, which is the wave function, but we'll come back to discuss that.
What I am asking is the e to the power I b dot p1, so only p1 appears, so are you fixing your p2?
No, this is just a convention about what I'm picking to be the center of the coordinates. It doesn't, I could also write this as, choose the center of the coordinates for B to be in the middle of the two, or choose it to be P2. It doesn't. Okay. Doesn't really matter. It's just a question of where the zero. So P2 here is chosen to go along the. Let's say if we're choosing B to lie entirely in the y direction. Okay. How I'm choosing my coordinates. Then that means I'm choosing P2 to be traveling along the x-axis, but at y equals 0. And I'm choosing P1 to be traveling in the opposite direction, again, parallel to the x-axis, but at y equals the absolute value of B.
Okay, thank you.
So, so we want to write a formula for the final momentum. And so now we have to write it, of course, in terms of the outstate. And we're just going to write the momentum operator. Oops, actually, let me put the subscript down below. So P1 mu. Of course, the outstate is not something that we control independently. It's something that's ultimately controlled. Actually, let me also write this consistent way. Sorry about that. But of course, given the initial state and given the knowledge of the theory, then we can write the outstate in terms of the evolution of the incoming state under the interactions that the theory gives us. And of course, that evolution operator from the far past to the far future is just given by the S matrix. So we can simply write, even if we don't have the detailed control over the outstate, the way that we've put in the instate, we can write it in terms of the instate. So now we have a formula for the outgoing momentum that, in fact, where we, in principle, know everything exactly. We have the and much of our discussion today and the first part of Friday morning will be understanding how to turn this formula into an integral which gives us, and then evaluate that integral, which gives us the classical result. So at this stage, it looks a little bit abstract, but we can insert a complete set of states in between the two appearances of the scattering matrix. And that allows us to write this final observable, final momentum, as a certain sum over states. And because we've taken particle 1 and particle 2 to have conserved quantum numbers that are independent, it means that every intermediate state that we put in has to have a net particle 1 quantum number of 1 and a net particle 2 quantum number of 1 as well. And we now have measuring that particle's momentum in this state that we put in. And of course, the thing then breaks up into a square. So we have a transition from our initial state to this intermediate state squared. So again, this is the incoming state, which we have specified. And this is our the intermediate state we would put in here, but you can think of it as the final state of the scattering process. So this is the outgoing state, in a sense, to the far future. And of course, we have to sum over all possible number of messengers. So if we're doing QED, it would be photons. If we're doing gravity, it would be gravitons. And of course, it also includes there being nothing beyond the two incoming particles. And finally, the other comment is that this sum includes whatever phase space integrals are associated with the extra messengers. So this tells us that we're going to be able to evaluate this in terms of scattering amplitudes. And so we can see, in a sense, where this is going. Now, here, it's been written in terms of plane wave states for the outgoing states. And in the quantum theory, that's fine. In the classical theory, ultimately, we probably would want to recover this in terms of localized wave functions. To do that in technical detail, or at least before you get to the classical limit, is actually quite challenging. And so we're going to want to avoid having to do that explicitly. We'll see how that happens as we go on. So we're not actually just interested in the final momentum. As I said, we're interested in the impulse, which is the difference, or the time integrated difference, of the initial momentum from the final momentum. So we want to take the outgoing and subtract the incoming momentum. But the incoming momentum is quite easy, because there we just controlled everything. We don't need to put in any additional scattering. So again, we can just write it in terms of our S matrix, our momentum operator for particle 1. And we just subtract off the, I may get tired of writing the in subscript, so if I drop the in subscript, it should be understood to be there implicitly. So the next thing to do is to realize that we can now simplify things, because the S matrix itself, in fact, the most, if we're working in perturbation theory, the most typical thing to happen is that nothing happens. The incoming state just merrily goes on and emerges, the same plane wave state emerges as the final state, and likewise if you have a superposition. And so if we have that unity contribution to the S matrix, that will just cancel between two terms. So we can take advantage of that to simplify our expression. We write S plus equals 1 plus IT. T is where the real dynamics are, the transition matrix. And we can now do a little bit of algebra, and we can write out, again, here I will drop the in suffix, in subscript on the incoming state. So we have terms that are kind of starting to look a little bit commutator-like. But there is still a quadratic term in the transition matrix. So that's something that where we would have to put in an intermediate state in order to express it in terms of amplitudes. And so we can now write this out in a form that makes this commutator structure a little bit more manifest. So the commutator has allowed us to shift the momentum evaluation to the same side. We still have our square term, but we can introduce a commutator there as well. And I guess I'm also dropping the mu's here. Let me put them back in. And we now have a sum of terms. So the momentum operator is now just hitting the right-hand side state. And so we'll notice there's a very nice combination this term, and this term. And it's a nice combination because we can write out the unitarity equation for the S matrix. So it's just going to be, these are terms that, of course, one could imagine calculating separately, but why calculate things that are ultimately going to cancel? So these terms will cancel, and that means that we can write out our master formula for the impulse in terms of these commutators of the momentum operator with the transition matrix. And there's two terms. And these two terms I will refer to as I1 and I2. Conveniently enough, I1 is linear in T and I2 is quadratic in T. So now we should play around a little bit with this expression. And we should start to plug in our formula for our form for the incoming state psi. And again, both of the psi's and essentially all of the psi's that will appear going forward are going to be in states. So it's not exactly a conventional S matrix element here where you're transitioning from an in state to some far out state. And it's good to keep that in mind conceptually. So let's start to write this out a little bit. So we have, of course, two copies of that incoming state. So there's one on the right-hand side, which I'll just write out. And this is the right-hand side appearance of psi. And I'll put primes to denote the one that appears on the left-hand side. And of course, there's phase. This phase factor is coming from both places. Oops. There. P1 minus P1 prime. And of course, there is the 1 over h bar. There's the wave function factors from both the right-hand side and the left-hand side. The momenta here are different, but the wave functions are going to be the same. One of them, sorry about that, one of them is conjugated. So again, this is from the right-hand side, and this is from the left-hand side. Then, of course, we have the actual operator that we're measuring, which is the momentum of the of particle 1, or the object that's carrying the charge corresponding to particle 1. And now we actually do have, finally, a matrix element, just a very conventional matrix element between plane wave states. So this thing, finally, we recognize as an object that we know and love. oops. This is a scattering amplitude. So this is something that we know how to compute, or at least those of us who have been working in amplitudes know how to compute. And at this point, this expression is in fact good to all orders in perturbation theory. Now, it's not good to all orders in perturbation theory standing on its own as I1. One needs to include I2 as well. So there are a number of things that are peculiar about this. First of all, it's linear in an amplitude, and we're not used to that. Physical quantities are usually quadratic in an amplitude. If we think about a differential cross-section, it's a tree amplitude squared, and then of course there are interference terms between loops and trees, but it's a quadratic kind of object. But any phase dependence cancels between the two copies of the initial state. And that's the other thing that's again a little bit strange here, is that it's linking two different copies of the initial state. So what we might think of as the momentum transfer in the initial state that then gives you the final state, actually it's something that I'm going to call a momentum mismatch to distinguish it from momentum transfers that we will actually see as we go on a little bit further. So let's do some change of variables here just to clean up, do a change of variables. So we're going to write QI is equal to the left-hand copy minus the right-hand copy, and that again is what I'm going to call a momentum mismatch. And this scattering amplitude here, I should say that of course it also includes a delta function. So in addition to the amplitude itself, so just to write out that formula, so we have from the amplitude point of view, it looks as though one copy is indeed the incoming state and the other is the final state, but that's not the physical role that they're playing. So I'm using slightly non-standard conventions here from an amplitudes point of view, where the momenta are not all directed outwards. They're directed as they actually are in real life. If we take into account this change of variables, then we have P1 plus Q1 plus Q2. And the delta function, very conveniently enough, just involves the sum of these two momentum transfers. And that means that we can integrate over Q2 using the momentum, using the delta function. And after I do that, we can then relabel Q1 to be just Q, because there's only going to be one of it that's left over. So let's see what that gives us. So again, we're still just looking at the first of two terms here in our expression for the impulse, the integrated change of momentum. So we still keep these phase space integrals over the one copy of the incoming state, but we're trading off the second copy for integrations over Q, and then we do the over Q1 and Q2, and then we do the Q2 integral. So we now have a residue from the on-shell delta functions for the primed variables, and we can write those out as follows: P2.Q minus Q squared. And then there are some theta functions which actually will not play such an important role, but of course you have to keep in mind they're there until we actually take the classical limit. And the phase factor, conveniently enough, is now expressed in terms of this momentum mismatch. We still, of course, retain the wave function factors. So we have, you can see there's a slight that the overlap of these wave functions is disturbed by this this momentum transfer. So you can start to think, if we imagine some very tightly peaked wave function, that it's going to force the contributions to come from small q in order to make sure that the overlap of these wave functions is large, and that we get a large contribution to the integral. Finally, we have the observable that we're measuring, again expressed in terms of this momentum mismatch and our amplitude. So it's nice to write this out also in diagrammatic form. And we can write that as follows. So of course we have the same, if you like, dressing that is coming from the measure. Let me not write that out explicitly, but you should just visually carry it over from that first line. And we'll then have the phase factor. That phase factor will accompany us all the way to the very end. We have the observable that we're measuring, and we can now write in diagrammatic form. So the wave functions here are dressing the diagram. We have, from the amplitude point of view, what looks like an incoming state. And from the amplitude's point of view, outgoing states that are offset by this momentum mismatch. And again, I will emphasize that this is in principle to all orders in perturbation theory. So if you want to think of this diagrammatically, you should be thinking of this as a sum that includes the tree and loops and two loops and so on and so forth. Again, we'll see in a minute that the tree amplitude actually has, from this contribution alone, has independent meaning, but the other terms will only be meaningful when combined with I2. So, of course, that means that inside these diagrams, if we have, for example, a loop diagram, there will be multiple messengers, photons for QED, gravitons for gravity, that are exchanged, but all of those will show up as virtual particles. Now, the lowest order contribution, we can see, if we think about it for a second, of course, there's going to be a tree. So that's going to be order g squared. And when we come back to I2 in a minute, we'll see that there is actually no contribution of order g squared. So this is an order that has to appear. Of course, that's the first order in the classical scattering. And that contribution is special in that it comes only from I1. But more generally, you have to include both terms. So let's, in fact, go ahead and look at the second term. So, and again, let's introduce a complete set of states. So again, we're going to introduce, there has to be one net one particle of type 1, net one particle of type 2. And there can be a lot of other particles. There could be, in the full quantum theory, of course, there could be a whole tower of both massive and massless states. But the most interesting thing is just to consider the X here containing some number of messengers. So I2 here, we can just write it out. And it is here we need to introduce the these intermediate states just to write it in terms of amplitudes, not merely for conceptual clarity. So again, we have sum over states, and that sum over states implicitly includes the phase space integrals that are associated with additional particles. And it also implicitly includes the case where there's actually no additional particles. We just have the particles we start with. And actually, let me...
David, there's a raised hand, actually. I think
just to give me 1 second here, let me do it in a slightly more abbreviated form here. Just 1 second. So let me finish writing out this line. So we now can put in this intermediate state. And once we've done that, these, of course, in principle, we could find a set of states that have wave function factors. But here, since we're just doing a complete sum, it's easiest and most convenient to do this in terms of plane wave states. Also, we don't have to go through the trouble of trying to find wave functions that give us a complete set of states. Yes, there was a question.
Hi. Could you comment something on the phi? Are these like Gaussian wave packets?
You're talking about the little phi, the wave functions?
Yeah, yes.
Yeah, so for the moment, in fact, you can think of them as kind of being the relativistic analog of Gaussian wave functions. I was actually hoping to get to that today, but I think we will have to do that on Friday. We'll see how to write down relativistic wave functions that are, morally speaking, although not literally, Gaussians, but conceptually you can think of it that way. There are things that localize the particles, and in the classical limit, of course, they will be localized both in position space and in momentum space.
Okay, so the amplitudes that you are obtaining here, like, are these like some kind of dressed amplitudes? Because in the previous slide you showed like the 4 legs, they have like dressings with phi kind of things, right?
No, so it was of course the explicit integral formula that I wrote is the truth. The diagrammatic thing essentially is telling you that you take the plane wave amplitude. It's a conventional amplitude that you calculate the quantum field theory course or using amplitude methods, and then you integrate that over the P1 and implicitly P1 prime, P2 prime phase spaces with a weighting factor that's given by the wave functions phi1 and phi2 of P1 and P2 respectively. So in that sense, they're dressed, but they're dressed by the wave packets.
I see. So amplitudes that you obtain, like, are these free of infrared divergences if you do tracing like this way?
So the tree amplitude, of course, is free of infrared divergences.
Yes.
And that's part of why I1 and I2 don't really have any meaning independently. It's getting a little bit ahead of ourselves, but imagine that we go beyond leading order. What's going to happen is that we're going to get a one loop contribution from I1, And we're going to get what's essentially the equivalent of a tree squared, integrated tree squared from I2. Each of those will have infrared divergences, but they will cancel. And that cancellation is not identical, but it's similar in spirit to what happens in conventional cross sections.
Okay, thank you.
Okay, so so again, here we had to introduce the initial states in order, the intermediate states, excuse me, the complete set of states, in order to be able to write things in terms of amplitudes. And in view of the time, let me just write out one key formula, and I will postpone the discussion, or even the beginning of the discussion, of the wave functions to Friday morning. So so I'm going to run just a few minutes over, but so apologies for intruding into the discussion session. So again, we can write out our incoming wave function, and we can change variables, and we can integrate out one of the variables and relabel them. And we have then a formula for I2, which is the analog of the formula for I1, except that it's has the sum over additional particles x. And again, of course, the lowest order contribution has nothing extra. We now have the we have to, of course, integrate over both of the incoming particles. We have the integration over the incoming state, the integration over what here genuinely is the final state. There's an integration over the momentum mismatch, and the same kinds of on-shell factors inherited from the P prime on-shell phase space measure. So P2 minus dot Q minus Q squared, and then the theta functions. And again, of course, the wave functions, these wave function factors, which will flesh out on Friday morning. So they are shifted in the copy by the momentum mismatch. We have, of course, our phase factor, and now it really looks like the difference of final and initial momenta. And we have, of course, a energy momentum conserving delta function that looks normal in the usual way. And again, for the lowest order contribution, actually, let me write this as a momentum. It has if there's no x, Rx is just 0. And now we have, of course, there's two matrix elements, and so we have two copies of amplitudes that go into x, and they start from different copies of the, and in one case, slightly shifted copy of the initial state. So here, R1 again and R2 really do represent the initial state, and Q is again a momentum mismatch. And I will postpone a diagrammatic presentation of this until Friday morning, but it's a good exercise for you to write it out and see if it matches what I put up on the board then. So let me stop here, and if there's time for additional questions, now's the time for them.
Any questions?
In this expression in the last line, the A star, the arguments, will it be P1 plus Q and P2 minus Q?
I'm sorry. Thank you for catching that mistake. Very good. I'm glad I didn't do that deliberately to see if people were paying attention, but yes, it is. That is correct. That was a mistake, a typo.
I just had a quick question about your I1 quantity. Is there a way of seeing whether or not it's supposed to be real, its reality? Because it's, like you said, it's linear in the amplitude, but corresponds to an observable quantity. So,
well, I think at lowest order, where it's the only contribution, yes, you can follow through an argument from the tree amplitudes. At higher order, there's cancellation of imaginary parts between I1 and I2. So it doesn't actually have to be real on its own.
thank you.
I have a question. Okay, sorry. So like this momentum transfer, whatever you defined, so is that the momentum transfer I should think of due to the forces acting between the 1 and 2 particle, or also it includes the radiation back reaction effect that due to radiation energy loss, there will be some momentum change?
So that's an excellent question. And in fact, this at the lowest order, there is no radiation. The radiation, as we'll see, starts at order G to the 6th, which is equivalent to next to leading order. But these are all order expressions, and at higher order, yes, P1. So the question, in some sense, one way of answering that question is to say, what happens if I compute not only the impulse of particle 1, but also of particle 2, and also the net momentum radiated? And what you'll find is that at lowest order, the impulse of particle 1 is equal and opposite to the impulse of particle 2. But as you go to higher order, that equality will be broken, and it will be broken precisely by the net momentum that's radiated.
Okay.
Okay, I think we'll reserve any further questions for the Slack channel. I see there's one that's just popped up on there now. But because we're overrunning, I think we should thank David for these lectures.
Thank you.